loving Father in heaven, we thank you, Lord, for all the blessings we can be here today. Now we're going to start chemistry class. Please bless us, bless us the teacher. Give us cleverness and wisdom. Forgive us for our sins. In the name of Jesus, pray. Amen.
Good evening. Good morning, friends.
Para sudah sedang tes. Oke, saya sebelumnya mau tanya dulu siapa yang nggak masuk hari ini? Dan sakit. Santa? Kenapa Santa?
Tidak tahu.
Oke. Hari ini kita mau melanjutkan materi yang kemarin, yaitu kesetimbangan kimia. Kemarin kita udah belajar tentang faktor-faktor yang mempengaruhi kesetimbangan. Apa aja? Good. Bagus. Dapat. Sekarang saya mau masuk ke materi tentang menghitung kesetimbangan itu. Bagaimana menghitung konstanta kesetimbangan? Boleh dinyalain dulu.
Pengen rusak itu.
Ini ada video tentang kesetimbangan. Nggak sesusah yang dibayangkan.
Turn off the light, please.
Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 65. It's on the equilibrium constant. A chemical weapon that was used in World War I and killed a number of people is phosgene. Phosgene is created through a reversible reaction where you take carbon monoxide and chlorine gas, you mix them together, and you get this phosgene. And this is a World War II poster warning people that this chemical might be coming. It gives off a smell kind of like hay. And since it's colorless, that was an important way for you to know that this chemical might be coming. And so in any kind of a chemical reaction like this, it's reversible. The reactants are converted into products, and the products are converted back into reactants. But it's important that we know, do we have more reactants or do we have more products? And so we use our K value, or equilibrium constant, to figure that out. In this chemical reaction at standard temperature and pressure, we're going to have a really large K. What does that mean? This reaction is going to move towards the right. That means that we're going to have way more phosgene than we're going to have any of these reactants. And so in a reversible reaction, reactants are converted into products and back again. And over time, it eventually reaches an equilibrium. Now, what is K? K is simply a way to measure when we reach equilibrium. Do we have way more reactants or do we have way more products that are being produced? And so I've got this model right here that shows us how reversible reactions work. So there are going to be a bunch of molecules over here. We'll call those reactants, and they'll be green when they're on this side of the chamber, and they'll be red when they move over to the right side. This is a PHET simulation. Over to the right, I've created a K-ometer, which is going to measure our K value. So K is going to be the number of products divided by the reactants. In this case, we only have reactants on the left side, and so we have a very large number here, 100. And how many products do we have? 0. And so what's our K value going to be? It's simply going to be 0. So let me start this and see what happens to our K value. And so molecules are moving now from the reactant to the product side, from the product to the reactant side. But we basically have the same level on both sides, and so our K value is 1. Now as I tip it towards the right, we're getting more products, and so that is going to become a larger number up here, and so our value goes up to 3. We have about 3 times as many products. Likewise, when we pull it in the other direction, now we have way more reactants, and since our reactants in this case value is going to be around 75, products around 25, our K value is going to be around a third. Now this model oversimplifies a little bit because we only have products and reactants in this simulation. In a chemical reaction, you're going to have lots of products and lots of reactants. And so if we've got a reversible reaction like this, where this represents our reactants and this represents our products, this is the general equation for K. But if we were to figure it out for a more complex kind of an equation, this is the general way that we write out K, where K represents the concentration of one of our products, so that's going to be C, raised to the power of the number of moles that we have of that chemical. Likewise, it's the concentration of D raised to the power, and that power is going to be the moles of this product as well. Likewise, we're going to put the reactants on the bottom and simply the concentration raised to the mole. So look, what am I talking about? Let me show you an example of that. If this is our equation right here, this is going to be our equilibrium constant. And so what do we have? Well, here's going to be our products on the top. So it's going to be the concentration of water right here raised to the 2 power, because we have 2 moles out in front of that. Likewise, we've got nitrogen gas raised to the 1 power because we only have 1 mole of that. We're then going to put our reactants in the bottom. Likewise, both of these are raised to the 2nd power because each of those have 2 moles. Now, if I were to give you that reversible phosgene reaction, could you write the equilibrium constant for that? What's our K value going to be equal to? It's simply going to be equal to this. Well, each of these are raised to the 1 power because we have only 1 mole of each of these. So this would be our K value. Now, we can calculate K in the lab, and so at standard temperature and pressure, our phosgene is going to be this. This is going to be that value I showed you at the beginning, 4.57 times 10 to the 9th. What does that mean? We're going to have way more of this product than we do the reactant at that given point. In other words, you could write this number over 1 on the bottom, and it's going to show you how many of them are going to be the phosgene. Now, if we're to change the temperature, we can actually change that K value. If I change that temperature to 200 degrees Celsius, so if I change it and make it a really high temperature, you can see that our K value is going to be much lower. What does that mean? It's going to be shifted back towards the left, and we're going to have way more of those reactants than we do products. Likewise, if we were to take this equation right here, where we've got nitrogen and oxygen, and we're converting that into nitrogen oxide, what would that look like, our K value? Our K value is going to be simply this. It's going to be raised to the 2nd power because we have 2 moles of this gas. What is our K value for this equation? It's going to be a really, really small value. What does that mean? That we're going to have way, way more reactants concentration-wise than products, and so it's going to be shifted way over here towards the left side. Now, what if I were to increase temperature at this point? Let's say I were to have a strike of lightning, that's actually going to raise our K value and it's going to push it over towards the right side. Now, we know that in the atmosphere we have nitrogen gas and we have oxygen gas. But if we had a K value that was really, really large at standard temperature and pressure, all of this would quickly be converted into nitrogen oxide. But we know that doesn't occur. It only occurs when you have a huge amount of energy, a huge amount of lightning. And so again, in summary, if our K value is ever greater than 1, that equation is going to move from the reactants to the product side. We're going to have way more products than we do reactants. If it's ever less than 1, then we're going to have the reverse is true. We're going to have way more reactants than we do products. And so did you learn to use the values of K to predict which chemicals we're going to have when it reaches equilibrium? I hope so, and I hope that was helpful.
Terima kasih. Boleh nyalain dulu lampunya? Saya mau tanya dulu. Ini kan tentang pertama keseimbangan. Yang aku dapat dari video itu apa? Bisa nggak mengerti gambar? Mengerti gambar? Oke, saya tanya ke Des. Yang aku dapat dari gambar itu tadi apa? Video itu tadi.
Kalau K-nya sih tadi, pokoknya yang tadi dah. K-nya lebih dari 1, reaktannya lebih dikit, produknya lebih banyak.
Kalau K-nya kurang dari 1,
Reaktannya lebih banyak.
produknya lebih sedikit. Oke, tadi dia membicarakan pertama tentang phosgene. Ada yang pernah dengar phosgene nggak?
Tadi.
Ada yang pernah belajar Perang Dunia Pertama?
Udah.
Oh, nggak pernah belajar ya di sejarah. Perang Dunia Pertama, phosgene adalah gas yang digunakan oleh ilmuwan. Dia turunin dari pesawat, diturunin, jadi kayak bukan nuklir doang diturunin. Phosgene itu bentuknya bukan gas, dimasukkan, dijatuhkan. Nah, akibatnya apa? Phosgene itu bisa membuat orang ketika dia menghirup itu, maka dia akan mengalami gangguan pernapasan, batuk-batuk, akhirnya nggak bisa nafas, mati. Nah, pada saat Perang Dunia I, makanya tadi dia bilang phosgene itu baunya, kalau kamu lihat tadi dibilang baunya tuh kayak jerami yang habis potong. Yang tadi gambar gajah, lihat nggak? Ada gambar gajah. Nah, itu sebenarnya adalah dia kasih tahu pada zaman itu adalah peringatan yang dikasih tahu bahwa phosgene itu gas yang beracun
Produk pereaktan.
Yes, produk pereaktan. Apanya? Kalau tanda gini artinya konsentrasi. Yes, COCl2. Terus ada pangkatnya nggak?
Enggak.
Kenapa nggak ada?
Koefisiennya 1.
Koefisiennya 1.
Mol.
Terus oke. Nilai K-nya tadi dibilang besar. Kalau nilainya K-nya besar berarti produknya lebih banyak. Pada suhu ruang produknya lebih banyak. Maka dia bilang kalau misalnya mau mengurangi ini, dia harus naikkan suhunya dari 200 derajat Celcius. Itu yang dibilang pada video tadi. Makanya kita udah belajar kemarin faktor yang mempengaruhi keseimbangan, satu konsentrasi, yang kedua juga suhu. Jadi akan berkebalikan. Kalau suhunya dikurangi, misalnya dia akan ke arah mana, suhunya ditambahkan dia ke arah mana. Oke. Kalau misalnya saya buat reaksi kalau misalnya ada reaksi kayak gini, kalau saya mau mencari nilai K-nya, berarti caranya gimana?
Produk pereaktan. C pangkat C.
Good. Kemarin yang saya bilang kalau misalnya mau nyari ketetapan kesetimbangan, kesetimbangan itu ada dua macam fase yang tidak diperhitungkan. Apa aja?
Liquid.
Solid.
Good. Berarti sudah bagus pemahamannya. Sekarang saya mau lihat seberapa paham kalian. Kerjakan buku paket halaman 151 berdua. Halaman 151 nomor 1. Halaman 151 nomor 1. Kerjanya berdua ya. Nomor 1. Yes, ABCD. Dia cuma minta rumus buku kesetimbangan. Gimana caranya? Ya, kayak gitu. Oke, kita bahas ya. Nomor 1, Luki. 1A.
PCl5 gaseus plus kalsium dengan PCl3 gaseus ditambah klorida PCl2 gaseus menghasilkan konsentrasi PCl3 pangkat 1 dikali konsentrasi CL2 pangkat 1 per PCl5 pangkat 1.
Oke, good.
Katanya produk itu kok terbalik? Produk pereaktan.
Kadang tahu.
Produk pereaktan.
Ini produk.
Ada yang masih tidak sepaham? Jelas? Nomor 2, 1B. Iya terus. Langsung. Timbangannya nilainya gimana?
Konsentrasinya ya. Konsentrasinya jadinya SO2 CL2 pangkat 2 O2 per SO3 pangkat 2 CL2 pangkat 2.
Oke, good. Yang C. Aron.
Jadi gaseus gaseus CH3OH gaseus. Jadi konsentrasi CH3OH pangkat 1 dibagi konsentrasi CO pangkat 1 dikali konsentrasi H2 pangkat 2.
Oke, good. Yang D. Rizky lah. plus aqueous plus Zn solid reversible Zn 2 plus aqueous dan Cu solid. Konsentrasinya jadi Zn 2 plus per Cu 2 plus. Kenapa Zn sama Cu yang solidnya nggak dihitung? Karena solidnya dihitung tuh. Oke, good. Lanjut yang E. Chris. Trans.
1E 2NH3 plus CO2 reversible jadi NH2 CO2 NH4. Semuanya itu jadi 1 per NH3 pangkat 2 kali CO2 pangkat 1.
Oke, semua udah paham ya?
Yes.
Sekarang kita udah tahu nih cara menuliskan keseimbangannya. Kalau masih dalam bentuk rumusnya. Kalau misalnya cara ngitungnya, nah ini harus kita pelajari. Kita akan belajar menghitungnya. Kita lihat sama-sama dulu ya videonya.
Hey, it's Professor Dave. Let's look at chemical equilibrium. Sometimes chemical reactions are not unidirectional. They are reversible. The reactants create the products, which then go right back and create reactants. This means there is both a forward and a reverse reaction. When the rates of the forward and reverse reactions are the same, this system is at dynamic equilibrium. Chemistry is happening, but because the reactions are happening at the same rate, there doesn't appear to be any activity. There is a balance. We learned how to use stoichiometry to discuss limiting reagents and how much of the products to expect. But these were for unidirectional reactions where we assume that all the reactants make products and then the reaction is over. With equilibria, it's a little more complicated to calculate what the concentrations of each substance will be at equilibrium. So we're going to have to do a little bit of math to be able to describe the system. For example, let's look at this equilibrium. Let's say we start with 1 mole of PCl5, allow the system to reach equilibrium, and then once at equilibrium, we measure that there are 0.135 moles of PCl3. So how much of the other two things are there? To answer this, we can make something called an ice box. These letters stand for initial, change, and equilibrium. We set them up like this. For initial, we put the initial amounts of each thing. We started with just 1 mole of reactant, so we put 1 there, and zeros for the products, since there wasn't any of those at first. Then for the change, we don't know exactly how much the change was to get to equilibrium, so we call it X. For the reactant, we put negative X because it is being depleted. And in this case, all of the stoichiometric coefficients are 1, so as X moles of reactant are being depleted, X moles of each product are being formed. We would make these 2 or 3X as necessary if the coefficients were different. And for the products, X is positive because these are being formed. Then lastly, we add up the initial and the change to give the amounts present at equilibrium. For the reactant, this is 1 minus X, and for the products, it's simply X. We measured the final concentration of PCl3 as 0.135 moles, which here will correspond to X, and we therefore know all the other concentrations by plugging in X. Simple, no? Well, it can get trickier, as we will see. But first, let's learn about equilibrium expressions. Every equilibrium has an equilibrium constant, Kc. It will be given by the concentrations of the products, each raised to the power of their stoichiometric coefficients, over the concentration of the reactants, each raised to the power of their stoichiometric coefficients. This is called the equilibrium constant expression. One thing this constant tells us is whether the products or reactants are favored in the equilibrium. If Kc is much greater than 1, that means the numerator is bigger, so we are creating more products. If Kc is much less than 1, that means the denominator is bigger and we are creating more reactants. When we write this expression, we only take into account gases and aqueous species. Solids and pure liquids will not be included in the expression. For example, here, notice how carbon is not included in the expression, since it doesn't make sense to discuss a solid in terms of a concentration. Sometimes we may want to predict which way a mixture will go given some non-equilibrium quantities. To do this, we plug the non-equilibrium values into the Kc expression to calculate the reaction quotient, Q. If Kc is bigger than Q, Q is more on the reactant side, so it'll make more products to equilibrium. If Kc is smaller than Q, Q is more on the products side, so it'll make more reactants to equilibrium. When Kc equals Q, the system is at equilibrium. Let's try a more difficult icebox. Given the following information, calculate the equilibrium concentrations of each substance in terms of molarity. Remember that molarity is moles per liter. So we set up our icebox and calculate the concentration of our reactant. That'll be the initial value and 0 for the products. Now here, the change will be different for each substance because of the stoichiometry. For every 2 moles of reactant, we get 1 mole of each product. So we have to subtract 2x here and add x here. Then equilibrium is just the sum of initial and change. Plug them into the equilibrium expression and solve for x. Luckily on the right, both the numerator and denominator are squared, so we can take the square root of both sides. If it wasn't this convenient, we may have had to use the quadratic equation. But as is, we can solve for x and use that to determine all the equilibrium concentrations. Let's check comprehension.
Oke. Video tadi menayangkan cara kita menghitung keseimbangan kimia. Keseimbangan kimia kita udah tahu caranya bahwa konsentrasi produk atau konsentrasi reaktan. Tetapi tadi yang ditekankan yang pertama adalah kalau misalnya kita biasa di stoichiometry, kalau misalnya bahasa Inggrisnya dipakai icebox, ICE, kalau bahasa Indonesia kita biasanya pakai MRS. Nah, mulai reaksi setara seimbang selesai. Kalau misalnya kita pakainya adalah stoichiometry yang biasa, maka di sini biasanya reaktannya diharapkan habis. Di sini ada produk, ya kan? Tetapi untuk kesetimbangan, kalau kalian perhatikan tadi, di sini tidak boleh setelah setimbang nilainya habis. Ini nggak boleh. Misalnya di sini habis. Kenapa? Kalau nilainya habis, ketika kamu nilai K-nya kamu cari, maka per 0, bukan? Ya kan? Kalau per 0, maka nilainya berapa? Ya kan? Nah, kalau misalnya tahi enggak, maka ketetapannya enggak ada. Enggak tahu kita berapa, bisa negatif, bisa positif. Maka kesetimbangan tidak pernah ada yang namanya produknya habis. Karena dia bolak-balik, udah jadi ke sini, tapi ada sedikit yang balik lagi ke sini. Jadi nilai K-nya nanti tinggal dilihat, kalau lebih dari 1 berarti produknya lebih banyak. Kalau kurang dari 1 berarti produknya reaktannya lebih banyak. Nah, karena dia pakai Kc tadi, C itu singkatan dari apa sih? Konsentrasi, concentration. Maka kalau misalnya mencari concentrationnya ini, kamu boleh dari sini konsentrasinya langsung, boleh hitung mol dulu, baru terakhirnya jadikan konsentrasi. Oke, kita coba dulu soal buku paket. Halaman 151 nomor 2. Halaman 151 nomor 2. Oke, dalam blok tertutup volumenya 10 liter direaksikan masing-masing 0,5 mol gas nitrogen, 0,5 mol gas oksigen hingga membentuk reaksi setimbang. Jika pada saat tercapai kesetimbangan terdapat 0,3 mol gas nitrogen, hitunglah nilai tetapan kesetimbangannya. Pertama, langkahnya harus ditulis apanya dulu berarti? Kesamaan reaksinya dulu. Baik, mau maju? Tulis kesamaan reaksinya Pak. Kemudian mula-mula masing-masing berapa mol? 0,5 siapa aja?
Nitrogen dan gas oksigen.
Ingat, dia masih dalam bentuk mol ya. Kemudian kita baca lagi soalnya. Pada saat tercapai kesetimbangan terdapat berapa mol gas nitrogennya? 0,3 mol. Saya tulisnya di mana?
Di
Di S punya siapa?
nitrogen.
Nitrogen.
2 kali.
Sekarang kita akan menghitung. Kalau begitu R-nya berapa di sini? 0,2. Saya bikin minus deh biar kamu nggak lupa. Karena kalau reaksi ini berkurang, di sini bertambah. Oke, kalau di sini 0,2, di sini berapa? Kenapa?
0,1.
Kenapa 0,1?
2/1.
Yes. Kalau dia koefisiennya 2/1. Kalau di sini 0,2, di sini 0,1. Berarti di sini berapa? 0,4. Oke, sekarang N2O-nya di sini berapa? Lihat koefisiennya.
2.
Berarti jadi berapa? 0,2. Kenapa 0,2? Ini koefisiennya sama. Kalau di sini yang bereaksi 0,2 mol, berarti di sini yang bereaksi beratnya 0,2 mol. Plus. Maka setelah bereaksi dia akan jadi 0,2 mol. Nah, ini molnya. Yang tadi saya bilang kesetimbangan gak mungkin ada yang 0 karena yang namanya setimbang di kiri ada, di kanan ada, walaupun jumlahnya berbeda. Oke. Kemudian kita mau nyari nilai K. Kalau nyari nilai K kan harus bentuk konsentrasi. Konsentrasi itu cara nyarinya gimana sih? M sama dengan M sama dengan
MR.
Oh, M sama dengan N per V. Maka kamu masukin satu-satu. 0,2 per 10 pangkat 2. Karena ini koefisiennya 2 ya. Baru reaktannya 0,3 per 10 pangkat 2. 0,4 per 10 pangkat nggak? 1. Oke, tinggal dihitung. Oke, coba dikerjakan dulu. Berapa hasilnya?
Miss, itu kenapa M-nya dia 0?
Kenapa?
Kenapa M-nya 2 N 2 0?
Karena mula-mula ini kan direaksikan ini.
Oh,
Nggak
iya.
ada, tapi pas reaksi dia reversible. Oke, coba dikerjakan dulu hasilnya berapa? Ada yang dapat hasilnya?
Berapa? Enggak.
Berapa? Sama jawabannya?
5 koma.
Berapa?
5 koma.
5,5. Coba. Chris maju.
Lu kirain lu.
Kamu yang maju. Ayo, oke, coba Ki. Oke, thank you Lucky. Bisa? Enggak. Ada yang salah hitungannya? Tadi 3. Sepertinya pas di depan ya hitungnya baru benar. Oke.